All right, can you see my screen? Perfect. So today I'm going to talk about a project I'm working on. The aim is to design a nanocarrier for drug delivery, and it will be for the treatment of kidney disease, which is called idiopathic nephrotic syndrome. Oh, maybe. Yeah, I just move my screen. Just a question: do you see all the sorry, all the zoom parameters on the screen, or it's not the case?
Sorry?
Do you see only my screen or also the zoom parameters?
We are seeing your slides, yes.
Okay, perfect. Sorry.
Yes.
Yeah, so we are working on...
And I think it's already in projection mode.
Okay, perfect. Sorry.
No problem.
So yeah, we are working on the design of nanocarrier for drug delivery that will be used for the treatment of kidney disease, which is idiopathic nephrotic syndrome. We will talk about it later. And these carriers that we developed are based on chitosan nanoparticle with control properties, and especially control mechanical properties in order to improve the cell uptake. So when we start the project, the first question we ask is actually how can we improve on which parameter can we play to improve the cell uptake, and then get a treatment that is has a better efficiency. Just as a reminder, but I think everyone is more or less talking about bio application. The cell uptake is the action that of a cell to integrate external molecule, like a drug, for example, here, into the cytoplasm. And so knowing the interaction between the particle and the cell membrane, it's has a great importance for the design of a safe and efficient treatment in nanomedicine. There's different parameters we can play on, and they are represented here. There's first the size of the nanoparticle, their shape, their mechanical properties, the stiffness, and it's what we will especially focus on today. The surface, the external layer of the nature of the external layer of the nanoparticle is also important because it will allow interaction or avoid interaction with other molecule and the environment. And the last one is what is called here microenvironment. It's when the nanoparticle has the ability to change their behavior under stimuli. So during this presentation, we will especially focus on the mechanical properties that we try to design. But in my PhD, I integrate all these factors. So how the mechanical properties influence the cell uptake? Actually, if you take a soft particle, this soft particle will be able to deform, to pass through the membrane, compared to a stiff particle that will be from the same size. The problem we focus on, or the topic we focus on, it's the vectorization of therapeutic DNA that has to be delivered in the kidney cell in order to treat the idiopathic nephrotic syndrome. This syndrome, it's a degradation of the renal membrane, and it was identified that this syndrome was due to the overexpression of a protein called SEMI. And in collaboration with a researcher in medicine, they developed actually a therapeutic DNA that is able to inhibit the expression of this protein. And our job as a chemist is to vectorize this DNA through nanovectors. Working with kidney, it's a bit tricky because it's the organ of the filtration, so it's very selective, and the porosity is about like 60-80 nanometers. And actually, in nanoscience, getting particles that are monodispersed and with a well-defined size of less than 100 nanometer, it still remains a challenge. So the technique we decide to, or the strategy we decide to choose to elaborate the nanovector, it's based on the use of templates. This template is monodisperse, or is with a well-controlled size and polydispersity. Here, for example, during this project, we use gold nanoparticle. There are commercial one, so gold nanoparticle of 60 nanometers. And on this gold particle, we will add successively a polyelectrolyte of opposite charge to form a multi-layer film around the particle. So here the polyelectrolyte we choose is first the DNA, because the DNA is negatively charged, so is used as polyanion, but also as active principle in our project. And the other one, we decide to go for a polysaccharide, and that's why I'm here today in this kind of conference, because we decide to go for chitosan. We decide to go for chitosan because he's positively charged for acidic pH, but is also approved by the FDA for renal application in medicine. And we will also see later that there's another interest to use chitosan because of the ready functions that are already ready to, or easily possible to modify, and that has a strong interest afterwards in the project. So when the nanoparticles is formed with a polymeric film around, the template is removed, and that's allowed to have a particle which is flexible, a particle that we call capsule, and that is more flexible than the particle with a gold core in the middle. Then we decide to go for a biological assay to see if we can identify a difference in the therapeutical efficiency between the particles, so with the hard core, and the capsule that are more flexible. And actually, the result we get, it's that in presence when, oh, sorry. Yeah, so in vitro assay, we put like this capsule and particle in contact with kidney cells, and we were checking if they could inhibit the production of CEMIP, which is represented here. So here we see that with this capsule, the production of CEMIP is lower than if they are in contact with a particle, meaning that the mechanical properties has an influence on CEMIP expression, and then the treatment will be more efficient with capsules that are more flexible. So we could prove that the mechanical properties has an influence on the cell's uptake, but we wanted to go further and control in a more precise way the mechanical properties. Therefore, we took exactly the same strategy than before, but this time we modified it, the chitosan, by thiol chemistry. Why thiol chemistry? It's actually because it allows to kill two birds with one stone. I don't know if the right expression in English, but what I mean is that we could play on two parameters in the same time. On one side, we could control the mechanical properties thanks to a disulfide bond between the chitosan layer in the multi-layer film. Then it's allowed us to get intermediate behavior between the nanoparticles and which is stiff, and the capsule that is flexible. And on the other side, the addition of a thiol function allows us to do stimulus responsiveness, because the disulfide bonds are extremely stable in case of when they are in extracellular media, and they can be easily reduced when they go into the cell by a reducing agent that is naturally present there. So the second point is that we can do intracellular release, but I do not have enough time, so I won't talk about this part today. So come back to chemistry. The thiolation was done. The thiolation of chitosan was done by coupling with iminothiolan, and we decided to go for this kind of chemistry because it allowed us to keep charged polymer, which is important if we want to do layer by layer assembly. So here we evaluated the zetal potential of the chitosan, the thiolated chitosan, which is conserving. And then we also analyze the modification through X-ray photoelectron spectroscopy, XPS. And we can see the signal and energy binding corresponding to sulfur in case of the thiolated chitosan. If we go further in XPS analysis, we can see the energy binding corresponding to the thiol, but also energy binding corresponding to C-double-N function, which is due to the imidine that was added here. And also like this result were confirmed by other methods such ER, NMR, elemental analysis, and also the number of thiol were quantified by Hellman reactions that I will talk also later. So once we could prove that we had a thiolated chitosan, when we could prove that we had a thiolated chitosan, we played on the ratio of chitosan and iminothiolan in order to modulate the number of the percentage of thiol that was integrated in the chitosan. So it's what is represented here on the left. That is the ratio chitosan iminothiolan, and here's the percentage of thiol. And we can see that we were able to integrate an increasing percentage of thiol up to reaching maximal. On the other side, it's a zeta potential. This zeta potential is actually decreasing with the modification that was unexpected at the beginning. But nevertheless, the zeta potential that we have, it's good enough to conserve polyelectrolyte properties and to do the multi-layer assembly. So the next step was to characterize the mechanical properties by atomic force microscopy. So AFM, it's a technique that can be used to determine the topography of a surface, but also the mechanical properties. Therefore, force is imposed on the tip, and the resistance, the deflection of the tip to penetrate into the material gives information about the stiffness of the material. And the challenge actually with nanoparticles is that they are really small. And here we are talking about like 60 nanometers. And actually the size of the tip, it's about the same than the size of the particle. So there is a risk to have a shift of the particle by scanning, but also then according to where the tip will be on the particle, that to get actually versatile stiffness. Therefore, we decided to go first on a flat model, which will be a multi-layer film of DNA chitosan. For the elaboration of this film, it's exactly the same principle than for the particle. On the surface, chitosan and the DNA will be successively absorbed in order to form a multi-layer film. And this film will be then reticulated in order to determine the stiffness of the different film according to the percentage of thiol that was incorporated. So here are the results of the stiffness. So what we can see is that in orange, for a non-crosslinking film, the Young modulus that is representing the stiffness is about like 10 minus 3 gigapascal. And then for the for the cross-linking film with the lowest percentage of S8 thiol function, the Young modulus is already 10 times greater. And the value of the Young modulus for the different film is actually significantly increasing with the percentage of thiol, up to reaching a value that is 100 times greater than a non-crossing film. So through this result, we could actually prove that the thiolation of chitosan allows to provide films with a bright range of mechanical properties. A last result before going to the conclusion, it's that the stability of the film also, or more like the influence of the cross-linking on the film stability was evaluated by quartz microbalance. The principle of this technique is to look at the variation of the frequency according to the frequency is changing when you adsorb or you desorb materials. A gain of mass means a decrease of the frequency, and it's what we have on the left, where there is a multi-layer assembly of the film. So when we are building up the film, one film is with chitosan and DNA, and the other one is with thiolated chitosan and the DNA. So we could follow the construction of the film. Then these films, they were reticulated, and we put them in a media where they are destabilized. On one side, we can see that the film with the chitosan that was used as a control, there is a strong loss of material because the frequency is increasing, and this frequency is actually going back to the original frequency before building up the film. Means that all the film was actually destabilized. On the other side, the one with the film that was cross-linked between before and after the stabilization, there's almost no loss of or no change of the frequency, means that we have a stable film, and that the cross-linking allows us to stabilize the film. So to conclude, we were able to design mechanical properties thanks to the thiolation of chitosan. We could get a bright range of mechanical properties due to the incorporation of different percentages of thiol function in the chitosan. And as a further experiment investigation, the next step will be actually to do bioassay in the same way that the one I presented at the beginning. But this time we will do it with a particle with a different reticulation degree to see if the cell uptake is improved and what will be the effect on the therapeutic efficiency. And on the other side, a way or an investigation direction is to continue to work on the mechanical properties to better understand how they are working. So next step will be to do AFM, but this time on the particle, and also to do capillary electrophoresis and filtration to simulate how the particles they behave when they are going through a matrix. That will simulate actually when they are going through a membrane or into the blood circulation. Well, thank you for your attention, and if you have any question, I will be happy to answer.
Thank you very much, Fanny, for your talk. I have one question. Could you please go into more detail about the effect of the stiffness of your system in their efficiency? How the flexibility or rigidity of the capsule can affect their efficiency for drug delivery and for these applications?
Actually, if you have a particle or nano objects are more flexible. if the porosity is about, I don't know, 60 nanometers, a particle of 60 nanometer won't be able to go through, but actually a capsule of 60 nanometer can, because has more flexibility, so it can deform and pass through.
Pass through the membrane.
Pass through the membrane, so to get into the cell, sorry.
To get into the cells and deliver the cargo.
Yeah.
Okay. And do you have already any results about the incorporation of drugs, or you are more centered now in the chemical modification preparation of your capsules?
Like the next step that the bioassay that I will send next time, it will be with the chitosan modified with particle. And actually, because like this DNA, it's a therapeutic DNA, then the active principle is already on the shell of the particle. We don't need to encapsulate active principle; they are already in the shell of the capsule.
Okay, the one of the components of the capsule will act as the bioactive compound.
Yeah.
Yeah. Okay, I missed that. Certainly.
No.
Okay, thank you very much for your contribution. And since we arrive at the end of this session, I would like to thank all the speakers and congratulate them for their contributions for the success of this session about polysaccharides on biomedical applications. I would like also to acknowledge the invitation to participate as a chair in this session. It was enormous satisfaction for me to participate. And since we still have 2 or 3 minutes, I truly would like to encourage you to go into the website of EPNOI and see all the activities that we are engaged. Several of them are very interesting for young scientists. Please take a look. We also organize workshops, training schools. All these activities are very important for your formation and for establishment of collaboration. So take a look and some minutes to see what EPNOI is doing in different domains. So thank you very much. I think in 2